Hello, hello everyone. Welcome to the second webinar for this nano degree. Um, once, okay, so let's start our second webinar. Today, I'm going to discuss some key points of the first 2 weeks of the content that you learned in first 2 weeks. The RL framework problem, RL framework solution, and Monte Carlo methods. So let's get started. So first of all, what is the RL framework? What is this RL setting? It's just that there is an environment and there is an agent in that environment, and the environment presents the agent with a state. The agent reacts with an action. The environment gives presents a reward to that agent for that action and presents another state to that agent, and then the agent again responds with an action, and so on and so on. So the objective of the agent here is to maximize its re- reward and to solve this environment. Now there are two types of environments. One where there is a well-defined starting and end point. That's called the episodic task. For example, a game of chess which has an endpoint where one of the players wins. Another example of episodic task is a maze. An agent is in a maze, and he or she has to solve it and get out of it. So it has a starting point and an end point, a terminal state. The other kind is the continuing task. Um, you might have seen this in your first or second lesson. The agent has to balance this pole and keep balancing it as long as possible. So this task will continue forever. The the terminal state of this task is not uh, wished. The agent doesn't want this task to end. It has to be continuous. That's why this is called a continuing task. Now there are now I will just cover some basic terminology. Now the agent's objective is to maximize its cumulative reward. So one way to compute this cumulative reward is just to sum all the rewards of future states. The agent has to compute this in order to select action. So the agent can pick an action, pick the best action. One of the ways to compute is to sum all the future rewards. Another way is to use a discounted return, which is more in practice, which is more accurate. First of all, a discounting factor gamma uh, is between 0 and 1. So what the agent does is it gives less uh, importance to more later rewards than the more recent rewards. So if the discount rate is closer to 0, the agent cares more about more recent time steps, and it cares less about the distant future. If the discounting factor is closer to 1 or greater or closer to 1 or greater than zero point 0.5, zero point 0.6, the agent cares more about distant future. So depending on your environment, on your task, whether it is episodic or continuous, and how the rewards are defined in your environment, you pick gamma to be between 0 and 1, but closer to 0 or closer to 1, depends. Now all these things together define a Markov decision process (MDP). So, what is a Markov decision process? Well, it's defined by a finite set of states, S plus if it's an episodic task, because it includes the final state as well. That's the S plus. A finite set of actions, set of rewards for those actions, the one-step dynamics of the environment. Uh, Now, one-step dynamics means that the probability of getting ST plus 1 and RT plus 1 depends only on ST and AT. It depends only on one previous step. It doesn't depend on more historical steps. It only depends on one previous step. That's the one-step dynamics, and that is required for a process to be called an MDP. Another component is the discount rate gamma, which we discussed in the previous slide. So all these together are called define a Markov decision process. So a Markov decision process presents a problem to an agent that the agent has to solve. So how does the agent solve it? It is through a policy, by by finding a policy that will help the agent maximize its total reward. There are two kinds of policies: deterministic and stochastic. Deterministic, as the name suggests, has only one action given a state. The agent cannot pick any different action in a particular state. It has availability to only one action. A stochastic policy is the opposite. Given a state, the agent can have several actions. This is more realistic. Uh, so, and the stochastic policy here is defined as the probability of selecting a particular action given a state. So, this is more a realistic scenario, stochastic policy. Now, we'll discuss some value functions regarding this policies. For the deterministic policy, it's simple. The value function for the deterministic policy is called the state value function. It is just the expected return given a state S. Now, how do you compute this expected return? Is by taking the reward for getting into next state and then discounting the state value of the future state. So this can be simplified as RT plus 1 plus gamma times parenthesis RT plus 2 plus gamma times the state value of ST plus 2, and so on. So the agent, in order to determine the best action, has to compute a state value, value of a state, uh, and it's called a state value function. Uh, one one additional detail is that we take expectation here, because suppose an agent is in state S and it selects an action. Now, after selecting an action, the agent can land in many other states realistically. Uh, so we take expectation to uh, include the possibility of getting into all those states, and it's just a uh, probabilistic sum, so probability weighted sum of uh, the returns of all those states. That's why we take expectation here. Now let's discuss the optimality related to state value functions. First of all, vpi is what denotes a state value function. Now, a policy pi prime is better than or equal to a policy pi if and only if the state value function using policy pi prime is better than or equal to state value function of policy pi. This is to compare two policies. Now, to find an optimal policy, to determine whether a policy is optimal or not, it has to satisfy this condition, which relates us to this condition. So, for an optimal policy pi star to be an optimal policy, it has to be greater than or equal to all the policies pi. That means the state value function of pi star should be greater than or equal to all the state value functions of all other policies. Now, there is one detail here that this is not just greater, it's greater than or equal to. So, what that says us in terms of optimality is that there could be two optimal policies that have state value functions equal to each other, and they are both greater than all other state value functions. So that's what we say here. An optimal policy is guaranteed to exist, but it may not be unique. So there could be two policies that have same state value function, but that state value function is greater than all the other state value functions of other policies. And that state value function is called V star. So for example, here, as we have seen this in the lesson, now both are optimal policies because they both have same state value function, and it's greater than state value function of any other policy, but they are different. So if we take a closer look, the difference between these two is that from this state, this policy seeks to go up, action up, whereas here it seeks to select action down. But eventually, they all have the same state value function. Now, action value function. So, action value function is for stochastic policy. Uh, the expected return depends on not only just state S, but also depends on what action is chosen being in that state S. So it yields the expected return if this agent starts in state S, takes action A, and follows the same policy pi for all future states. This is important. Uh, and the optimal action value function uh, will be is called Q star. And once we have Q star, we determine the optimal policy for that environment uh, by just picking the actions for a state that has the maximum returns. So this will be more clear when we move on to Monte Carlo methods, and many of you have already seen that. Given a state, there are multiple actions, and we select that action which has highest return. That's what this argmax means. And we do this for each state, and then we put together all those actions selected for each state, and that makes up our pi star. That makes our optimal policy. So the important step in determining an optimal policy is to determine optimal action value function. Now, Monte Carlo methods. Uh, what we discussed previously, determining the optimal action value function is the problem, is the prediction problem in Monte Carlo methods as well. Now, what is the definition? Given a policy, how can the agent estimate the value function for that policy? So it is more of an evaluation step. Uh, it should be noted that we already have a policy here. It doesn't have to be optimal policy. It's just some policy, and we want to evaluate it by computing its action value function, and that's the prediction problem. Uh, and one of the steps of determining the optimal action value function given a policy is to compute a Q table. So how do we do that? Let's look into it. Okay, so this is the grid world example. Sorry, this is one of the examples from the lessons. And suppose we don't have any policy in mind, we just follow a random policy. So we use a random policy to collect many episodes, a large number of episodes, and then we note down the expected return for all those episodes. So when we start in first episode, uh, suppose the agent takes action A, it gets a reward of -1, and so on until the episode finishes. Once the episode finishes, we can compute the return for each state action pair this way. So +7 here is a return for only first state action pair, which is computed as 10 -1 -1 -1. That's 7. Uh, and this is just a simple example, so we are not using any discounting factor. Uh, Sorry, it's for set 0 action 0. If we have to compute uh, for S1 A1, it would be 10 -1 -1, that's 8, and so on. So we collected one episode. We do the same thing for many episodes. Now these are just 5 episodes shown here. In reality, uh, uh, we collect thousands of episodes, and we collect we compute expected return for each state and action pair, not just S0 A0 or S1 A1. It could be each state having all the 4 actions, and we compute expected return for all in each episode, and then we average over all the episodes. Once we average over all the episodes, we note that down in this Q table. I will come to this later. Uh, every visit versus first visit. So this is a Q table. Both are Q tables, and this is a state, and these are actions. And here we note down what was the expected return for taking action up, being in state uh, 1, and then we note down the average over all the episodes that we collected. Now, what is the point of this slide? So there are two ways of averaging these returns of each state action pair. One is every visit, that is in an episode, a state and action pair might be visited many times. So we take each of those visits into account in one episode, and then we take average of those returns for this state action pair. If it happens again, see here, it happened here once, happens here too in the same episode. I'm talking about the same episode. We take the average, and then we so in this table we are showing only for one episode. The average is taken over only one episode, but in reality we collect many of those episodes, and first we average for that episode, and then we take average over all the 1000 or so episodes, and then we update the values here in the Q table. That's for every visit. What happens in first visit is that we only take this into account, and then we put this value here. And again, this table only collected one episode, so they just put -87 here. In reality, you will be collecting many episodes, suppose 1000 episodes, and then take the average, and then you enter this value. So the basic difference is in the name for every visit in an episode, or just the first visit in one episode. Now, so this is a Q table that is generated after many episodes uh, have been run, and this Q table is used to estimate the action value for that policy. Uh, so when you are just starting out, you might have some values in the Q table, but it doesn't necessarily represent the action value function. So you have to run this Q table, run as many episodes as possible, and update this Q table as many times un until it stops changing the values and it stops changing the values, and then we say that it has converged, and that is the converged final table is the action value function of that table. So this is where our prediction problem has a solution. Our problem was to evaluate a given policy pi, and to evaluate, we have to find the value of action. We have to find the action value function, and this is it. So the action value function is just a function that gives out return of a particular state and action pair. So if this is our final action value function, Q of S3 and action down is going to be +8. That's that's how this random policy pi is evaluated. Now part two of our problem. We don't have we don't have to just evaluate a policy. We have to find the optimal policy. So what we have discussed until now is 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 just the policy evaluation step of the control problem. Now let me define the control problem. Control problem is given an environment, find the optimal policy. Don't just find the action value function or the Q table. We have to find the optimal policy. And one of the intermediate steps is policy evaluation. We have a random policy. We run many episodes. We update Q table, and we approximate the action value function. We do this until the Q table converges with the action value function, and that's the value of that policy. Then, once we have an action value function for a given policy, we improve it, we change the policy. How do we change it? This way. So let's say this is our action value function that we got from our random policy. Um and So we find the actions that maximize the return in each state. So over here, action up maximizes the return. So we select this. For state 2, it's right, and for state 3, it's up. So our new policy is select action up when you are in state 1, select action right when you are in state 2, and up in state 3. This becomes our new policy, and then we use this policy and run again a large number of episodes and then update the Q table. And we keep doing this. So we keep doing this as many times as possible, and eventually this will all lead to finding the optimal policy. That is the idea. So we update the policy, collect more episodes, update Q table, use the Q table to update policy, and so on. So in the previous slide, we are selecting actions which maximize the returns for that state. So this is called a greedy policy. They are only looking for the highest returns. But there are some drawbacks for this greedy policy as well, because you are only on you're only on one path. You are not exploring enough the environment. So there could be some, when you select this action, there could be some actions in the future states that might have higher expected return. But if you select only the higher actions with the higher returns, you you don't explore that possibility. So how we can improve our algorithm making is by adding a little element of exploration. So overall, we will be greedy. We will always look for higher returns, but we will also explore a little bit. We will keep some small probability to explore so that we don't miss out on some actions which have low return in this state, but they lead to actions that have higher return in the later states. So how we improve that is by using an epsilon greedy policy. So what is an epsilon greedy policy? Uh, we select a constant epsilon between 0 and 1, and we we modify our algorithm such that our agent will select the greedy policy with probability 1 minus epsilon, and it will select a random action, any action with probability pi, sorry, epsilon. So, so if our epsilon is zero point 0.6, so with 60% probability, the agent will select action up, and with 40% probability, it will select any action here. So each of these actions will have a 10% probability in that case. So the total probability for selecting action up will now be 70%. But this is just an example. So this is how we introduce an element of exploration in our algorithm, and it is very useful as well. Uh, so there are some suggestions on what values of epsilon to use. Uh, we can use a fixed value of epsilon. We can use a fixed value of epsilon, uh, but even then, we might miss on something. We want to be uh, exploratory enough in the beginning of our training, and once we have a lot of information about all the state action pairs, then uh, we exploit more. So that's the idea. So greedy in the limit with infinite exploration. The idea behind this is that to explore a lot at first and then exploit a lot in the end. And we are exploring for all time steps. So epsilon uh, will always be will always be greater than 0. Uh, so that is this way we can select values of epsilon. Now there are some suggestions on those values as well. So of course it has to be greater than 0 because we want to keep even a small little element of exploration in our algorithm. So the idea is that we decay epsilon to 0 as uh, our training approaches higher value. So we start with a higher epsilon, let's say uh, 1. So this is the most exploratory uh, scenario. It will select all actions, whether they are greedy or not, with um, equal probability. And then once we have gone through a lot of episodes or a lot of time steps in a particular episode, we reduce the value of epsilon. So this is one of the ways it can be implemented. So in your algorithm, you can um, put epsilon equals 1, and if you have a for loop for your iterations, and suppose number of episodes is the variable for the loop, you change the value of epsilon by 1 over number of episodes. So it's going to be 1 for the first episode, For second episode, it will be 0.5, 4, and then it will gradually decrease. And you can set limit on epsilon to be greater than 0. So it is always exploring a little bit. Uh, you can check out some academic papers which have very interesting implementation of this exploration and exploitation scenario. In the DQN paper by Google, they said uh, the decayed value of epsilon from 1 to zero point 0.1 for 1 million uh, episodes, and then after that they kept it as zero point 0.1. So it can also be done manually this way, or you can do it automatically as discussed here. So yeah, so the solution to the control problem is that you collect an episode with a particular policy, estimate the Q table, uh, approximate the action value function for that policy, then you change the policy to be epsilon greedy. So at first, if you will select randomly all any action given a state, that will be your policy in the beginning, but later on in your algorithm, your update to the policy will mostly be greedy. So this way, eventually, you will have an optimal policy. Okay, so there are some improvements suggested to the Monte Carlo method algorithm, which can improve the efficiency of the algorithm. It can make it faster to find the optimal policy. So currently our method is we have a policy, and then we collect a large number of episodes, and then we average over all those episodes for each state action pair, and then update the Q table. But if we can update the Q table after every episode, so instead of waiting for running all the episodes at first and then updating, if we can update the Q table after every episode, the convergence to the optimal policy will be faster. We will be able to find um an optimal policy uh, earlier, and it will also save us a lot of computational power, and it will be computationally more efficient. So let's discuss how this incremental mean can be introduced in our algorithm. So currently what we do is, for example, we collect these four episodes for one. Uh, so this is just for one state action pair. We collect four episodes, and once we have the expected returns for this four episode, we average them and we get our estimated action value. The improvement is that once we collect one first episode, we get it return, and that's the estimated action value. Then we collect the second episode, we get its estimated return, and then we update the Q table, Q value right away. Instead of waiting for all the episodes to finish, we update it right away. So how do we do that? Is by uh, adding the increment to the previous state action, previous Q value of that state action pair. So how do we compute this increment? Is by G, just it's a G minus Q over number of episodes. N here, it could be number of episodes, or it can also be number of visits to that state action pair. So I prefer calling it number of visits because we are updating it during each episode. So Q plus G minus Q over number of visits to that state action pair. So yeah, knowledge of estimated action value after each episode, and eventually if you follow this, eventually it does converge to the estimated action value that was computed here. So we are not doing something wrong. The only thing is that we can update our policy after every episode in this way. Yeah, this is again explanation of the same formula. Yeah, so now I'm going to just compare these two pseudocodes, what we did previously for, and this is for first visit prediction. So we computed the returns for all episodes, and then at the end of all the episodes we divided, uh, for each state action pair we divided its return by the number of visits to that state action pair. That's why I said calling it number of visits instead of number of episode. Mm, right. But now this time we we update it in every episode. So here, right, and then once we update it in every episode, we we go back to the loop, and then we can update our policy based on these values, these recent q values of all the state action pairs. So this way we get to update our policy during every episode. So this is how you can implement it. All right. So even this method of incremental mean has some issues. There are some problems. The problem is that when now in the beginning it's good if the number of visits to the state action pair are low, so we can increment this incremental value is large enough. But as we run more and more iterations in the state action pair, this number of visits, the denominator is going to be very, very large. And that's why it will bring down this overall value of the error or the increment that we are adding to our previous q value. It will bring down this value. So this is against our objective. Uh, we want the later parts of the episode, the information that we get from later in our training, we want to use that more than the earlier information, because at first we are just exploring a lot, and after collecting enough information we are getting some very useful information from the later episodes. So the point is that we have to replace this number with some constant, so that we can keep getting we can update our q value uh, with this future information, we so we can control how much emphasis we give to most recent values as compared to more historical values. So in this case, uh, we are not getting enough information from most recent values. So how to fix this is by introducing a constant. Uh, it's called alpha. And yeah, so later time steps are more important in estimating the action value. So we want to control how much emphasis we give to the later time steps. And this is how it is implemented. Now there is one variable less here, that is the n, the number of visits. We don't need that anymore. We just need this alpha, and then it can, with alpha we can control how much information from the recent steps come to us. And there are some suggestions for the values of alpha. Definitely it has to be greater than 0. If it's 0, then we don't take any information from the next steps. We rely only on we rely on randomness. So definitely greater than 0. And it has to be less than 1, because if it's 1, then the agent will care only about the next time step, and due to randomness, the this value can fluctuate a lot. So it can lead to not converging to optimal policy at all. So it has to be less than 1 and greater than 0. That's the first. Now, if it's a small alpha, the agent cares more about the long history of return than the most recent return. Uh, on the contrary, if there is higher alpha, agent focuses more on the most recent return. Um, if it's too low, slow learning, of course, again the same thing. And if it's too high, it will diverge a lot. There will be lot of fluctuations, so that it will never, or it will have difficulty in converging to the optimal policy. So the more the most useful value of alpha will have to be decided by trial and error. So it depends on your environment. Some of the environments might have low alpha useful, some might have higher alpha useful. It depends on your environment, and you'll have to try a lot and figure out that optimal value of alpha. So there you go. That was all in this webinar. We discussed the basic key points of the RL framework, problem, solution. We defined what is a Markov decision process, and then we discussed Monte Carlo methods, the prediction problem, the control problem, and how to solve it, and what improvements can be made to it, how we can introduce exploration in our algorithm. So that is all from my side. If you have any questions, feel free to ask me now. The recording of this webinar will be available on Slack channel, and feel free to watch it and summarize the key points. And you can ask me anything on the Slack channel anytime. Uh, so I will wait for a minute. If there are no questions, I will end this broadcast. Okay, so thank you for watching this webinar, whether live or the recording. And I hope this information helps you in your courses in understanding the content of the nano degree. Monte Carlo methods is very useful in some of the future projects in estimating the action value. So if you want to review Monte Carlo methods later, feel free to review it. You will need to review it, and so I will end this webinar now, and I will stop the broadcast. So thank you for watching this.